The economic production quantity problem is an extension of the economic order quantity. The primary difference is that in the economic order quantity, the items are ordered and show up instantaneously when delivered. So the inventory goes from whatever position it's in to the maximum inventory instantaneously. With the economic production quantity, the inventory is built over time as the item is produced internally and in-house. So the nature of the inventory pattern is different, and this requires a modification of the economic order quantity formulas. There are 3 videos that present the context for the economic production quantity. The first is a video on production of toaster pastries, which shows a very complicated production process. For scheduling purposes, this operates like a single machine or work center. The next video is an illustration of the injection molding process. This video shows how plastic pellets are heated, then injected into a die. The plastic cools and then is discharged as a completed part. The third video shows injection molding using a multi-cavity mold to produce plastic bottle caps.
For people who need to grab a quick bite for breakfast, the invention of the toaster pastry in the 1960s was the greatest thing since sliced bread. Finally, the toaster could be used for more than toasting bread, and the toaster pastry was definitely a sweet alternative. The toaster pastry retains its sweetness during toasting. The syrupy filling and frosting don't melt out and into the toaster. It's all because of the ingredients and how they come together. At this factory, they start by making an organic pastry. The blender operator loads dry ingredients like rice bran into the blender, followed by a sugar syrup and molasses. It's the molasses that gives the pastry a brownish color. He adds organic palm shortening and organic granulated sugar. The flour and water are piped into the blender barrel. Spiraling mixers blend and knead the dough to the desired consistency. Next, it's into a hopper that feeds the dough between 2 rollers. They squeeze and flatten the dough into a sheet that's about 0.8 of an inch thick. A conveyor moves the toaster pastry dough forward to sets of larger rollers. They apply serious pressure to roll the dough much thinner. Wheels at the sides fold back the dough as the width expands. A dusting of flour to the rollers keeps things from getting too sticky. Coming off the final rollers, the thickness of the dough has been reduced to 0.2 of an inch. At another station, they've whipped up a batch of cherry pomegranate jam. The jam is hearty and thick, so it won't run, as nozzles pump the jam onto the rolled pastry sheet. Each toaster pastry receives 3 strings of jam. This depositor system fills 10 tarts at a time. It works out to 390 tarts a minute. A second sheet of dough heads towards the jam-filled one. En route, a spiked roller punches holes for venting steam during baking. Without these holes, the pressure would build and the toaster pastries would explode. The top sheet of pastry now merges with the bottom one. The conveyor belts move at exactly the same speed, so the top pastry lands in perfect alignment on the jam-filled one. A cylinder with a brass grid pattern bears down on the pastry to compress it between the jam fillings. This forms pockets of jam. A cylindrical blade slices the pastry into individual tarts. A device pulls off the side trimmings. The toaster pastries travel through a 150-foot-long convection oven heated to 300 degrees Fahrenheit. The operator keeps a close watch for leaking jam. That would be a sign of bad seals in the pastry pockets. He rejects any with leaks. He also keeps an eye on the color as the pastries brown. They shouldn't be too dark or too light. Fresh out of the mixer, the pink frosting now flows onto a revolving belt that spreads it onto the toaster pastries at just the right thickness. They've added a bit of starch to the icing. And it's this starch that allows the icing to harden and set, so it won't melt and drip into the toaster during toasting. They sprinkle granulated colored sugar onto the toaster pastries. They call this topping the crunchlets. The crunchlets add both flavor and texture to the pastry. Once cold, the toaster pastries transfer from one conveyor to another. A breaker roller snaps them at the crimp line to separate them into groups of 2. The completed tarts head towards the packaging line. An operator does a visual inspection as they pass by. Mechanical arms push the tarts into aluminum wrapping. Hot rollers seal and cut the wrap at the ends. This wrapping preserves the tarts for 8 months. No preservatives needed. Suctioning arms grab and open cartons to accept the foil-wrapped toaster pastries. It takes about an hour to manufacture a box of toaster pastries. And now, it's time for a toast.
In the economic production quantity problem, machines are run intermittently. Theoretically, inventory is at 0 when the production process starts, and inventory is built to a maximum level. At that point, the machine is turned off, and this maximum inventory is used to satisfy demand until the inventory gets back down to 0 and the process is started again. We look at this triangle, which is different than the economic order quantity triangle, because we are building the inventory at a rate rather than instantaneously having the inventory show up. And the EOQ, we have the maximum inventory that we then consume until the next order is placed. In the economic production quantity problem, we're building up this inventory level. To understand this problem, we have to separate this triangle into 2 periods. The production period, we're building up the inventory, and the demand period, we're living off the inventory. The sum of these two is the cycle length, and that tells us how long we go from starting the manufacturing process until the inventory gets back to 0 and we start again. T sub P and T sub C are really the 2 important parameters for understanding this problem. Again, because the items don't show up instantaneously, the maximum inventory level is less than the production quantity because we are consuming these products as we are building them. What we want to get first is the average inventory. We want to find I max divided by 2 because we're going from 0 to the maximum back down to 0 in a linear fashion. Again, this is an idealized problem. We're not assuming any variability in production or demand, so it's going to be a simple matter to get the average inventory once we know the maximum inventory. And the key is we're producing and consuming at the same time. To understand the economic production quantity problem, we have to look at demand rates. I'm going to use the lowercase d to define the demand rate. The rate at which we're selling products could be units per hour, units per day, units per month. And the production rate, a lowercase p. So we're using lowercase variables to define these rates. Again, units per period of time. And as long as these are consistent, whether it's units per day or units per hour, it's fine. It could be units per year. We're just comparing the rate at which we can produce to the rate at which their product is demanded. And as long as we can produce faster than we can sell it, or the production rate is larger than the demand rate, we don't have a problem. In the real world, there are some challenges with calendaring issues and what the production rate actually is. But by and large, if you take it over a longer period of time, you can get a pretty good estimate that can be used in this problem. The key to the economic production quantity problem is to determine the maximum inventory level. And so, first of all, we're going to base this on the production quantity. In other words, how many units are we going to produce during a production run? So suppose Q is equal to 1,000. So we're going to turn on the piece of equipment and produce 1,000 items. Suppose the production rate is 100 units per day. And suppose demand is 10 units per day. This is important that our production rate is larger than our demand rate, otherwise we would not be able to build up inventory. Given these parameters for a problem, if we're producing 1,000 units, and we can produce it at 100 units per day, then our cycle time for production, or production period length, is going to be 10 days. Similarly, if we're producing 1,000 units at a time, and over this period, we're consuming 10 units per day, our production cycle is going to be 100 days. In other words, T sub C would be equal to 100. T sub P would be equal to 10. So we're going to be producing for 10 days, building up the maximum inventory, and then turning off the piece of equipment, and for the next 90 days, we will live off that inventory. To get to the maximum inventory level, it's the difference in the production to the demand rate times the production time that tells us what our max inventory is. So if we have 100 minus 10, which is 90, that's the rate at which we add to inventory every day when we are building up inventory. Then if we multiply that by the period of time that we're producing, T sub P, which is 10, this will give us 900 as our peak inventory. So we're going to produce 1,000 parts, and it's going to take us 10 days to do this. During those 10 days, we're selling 10 units a day, so we're going to sell 100 of those off. So at the point where we turn off the piece of equipment, the maximum inventory is going to be 900. So again, this is a key formula. The production rate minus the demand rate is the net rate at which we are adding to inventory. We multiply this by the period of time at which we're producing, and that's going to give us the maximum inventory. We just substitute for the production period, T sub P, the definition that it's the production quantity over the production rate, and with a little rearrangement, we have a formula for the maximum inventory. Again, this relationship is key. The production rate minus the demand rate times the production cycle time, T sub P, gives us our maximum inventory. Given this information, all we have to do is divide by 2, and we get the average inventory. So we take Q times the production rate minus the demand rate, divided by the production rate, divided by 2 gives us our average inventory. If we substitute this into the total cost equation, this is very similar to the economic order quantity. The difference is that S in this case represents setup costs, the fixed cost for producing a batch of items. This could be any labor that's specifically for setting up the piece of equipment, any bad production as the equipment's being tuned. It's a little bit difficult to come up with a correct setup cost. Frequently people look at opportunity costs, and an opportunity cost is what do I lose by doing something else? If your production facility is maxed out, in other words, demand is exceeding your capabilities, considering opportunity costs makes some sense. If your facility is not running at peak output, if you have some idle time in terms of meeting all the demand, then opportunity cost does not make sense to include. It's important to remember that opportunity costs are not real costs. If we look at this total cost equation, understanding that S represents a fixed cost that is different for the internal production process than for procurement, we have the same formula as the economic order quantity, except for this term, P minus D over P. This term is a correction term. It represents the difference in the max inventory because we're not instantaneously receiving the inventory but building it up. This correction term represents this green shaded area, the inventory that we're not holding because we're slowly building up inventory rather than having it show up instantaneously. Through the miracle of calculus, we can get the economic production quantity, Q SAR, the optimal production quantity, considering the setup cost, the fixed cost of setting up, and the inventory holding cost. And you'll notice the first portion looks exactly like the EOQ formula. It's just multiplied by this correction term, which now is underneath the square root. So we have P over P minus D. P is always going to be larger than P minus D. So the economic production quantity would be larger than the quantity we'd calculate just using the economic order quantity. This correction term deals with the fact that we don't have that excess inventory because we don't instantaneously receive the order, but we build it up over time. One thing that's useful to do with a mathematical equation is play some hypothetical games. What if? What if the production rate speeds up so it gets closer and closer to infinity? In the case the production rate is close to infinity, P and P minus D are not much different. If you're getting paid $100 million and somebody wants $1, that doesn't leave you much different off. It's different than if you only have $10 and somebody wants one of them. So as the production rate gets to be infinity, the difference between this and the production rate minus the demand rate is negligible. And the EPQ is just the EOQ formula. That makes sense. If the production rate is infinite, this is like a Star Trek replicator. This is like ordering it and it shows up immediately. We really don't have a ramp up of inventory. So the equation makes sense in this case. What if the production rate gets closer and closer to the demand rate? In fact, what if they're equal? Right? Well, the production rate equals the demand rate, then this denominator term is equal to 0. And mathematically, that means that this correction term is infinity. If you put this in Excel, you usually get an error. So as the production rate gets closer to the demand rate, the economic production quantity gets closer and closer to infinity. Does that make sense? Well, yes, it does. Suppose if the production rate is the demand rate, then we have to turn on the piece of equipment and we can never build inventory because we're selling it as fast as we produce it. So the economic production quantity formula says, at that case, we're going to produce an infinitely large quantity. Here's an example. Suppose our demand rate is 4,000 cases per day. Our annual demand, assuming we run 365 days a year, is 1.46 million, 1,460,000. Our production rate is 12,000 cases per day. It's important that the units of measure are consistent. We could use cases per year or cases per day. It doesn't make any difference as long as we're consistent. Next, we have the holding cost, which is going to be 20% of our item cost. So that gives us $5.694 per unit per year. And the setup, everything involved with getting the production equipment set up, any lost scrap material as we're doing this, totals $10,000. If we put this in the economic production quantity formula, we have the first part that really is the same as the economic order quantity and the correction part, and that gives us $87,706. This example is actually the example from simulation scenario number 30.